In this video, we're going to apply the fundamental theorem of calculus to find the area under a graph or evaluate an integral, but we're also going to check that we're getting something that makes sense by also calculating the area in another way, a more traditional way. We'll focus on a triangle because we do have other ways to find the areas under triangles. We've got a graph and we've got two bounds, x equals 0 and x equals 4. So let's go out to 4 here. The graph of y equals 4x is actually going to be pretty steep unless we change our axis scale. So let's just draw it like this. And noting that this would be 16 at the point y equals 4x when x equals 4. And we're actually going to tweak this to be y equals 0. So it's this horizontal line here. And that will give us this area here. And we already know that that area is going to be equal to the area of a triangle, 1/2 base times height. We know the base here is 4. And we know the height is 16. That'll be 64 over 2. That'll be 32 square units. Alternatively, we also know that that area can be defined by an integral. It's the integral from 0 to 4 of the function 4x dx. And now we can use the fundamental theorem of calculus to work with this. This function is what we call little f of x. And we want a big f of x, an antiderivative. Well, using our skills from earlier videos, we would want an expression like 4x add 1 to the power gives us squared, and divide by the new power and add a constant. This would be an antiderivative of 4x. Then we can evaluate our integral. This is a hard thing to find, at least in principle, but the fundamental theorem of calculus says once we have this, we just need to plug in the upper limit and plug the lower limit into this formula. So we're going to have f of 4, plug in a 4 here, we're going to have 4 times 4 squared over 2 plus c minus f of 0. That'll be 4 times 0 squared over 2 plus c. And that is 16 times 4, hey, over 2. That sounds an awful lot like 32 plus c and minus c. And we get 32 again. Definitely not a proof that the fundamental theorem of calculus is true, but certainly a confirmation that on this simple example, we get the same value through two different methods. So that makes us happy. Let's take a look at a second example. We have an interval, x equals 0 to x equals 5. We have a parabola. Here we won't know exactly what this area is through any other method except the fundamental theorem of calculus, but with some faith and trust in the hundreds of years of development of the mathematical technology behind this, we would say that the area we're looking for is defined by the integral from x equals 0 to x equals 5 of 6x squared dx. This is our little f of x. And so our antiderivative, big F of x, capital F of x, is going to be a 6 multiplier we keep around, x squared. The rule for powers of x is add 1 to the power, divide by the new power, and tack a plus c on the end. That's our side calculation. The area then is equal to this function, f at the upper limit 5 minus f at the lower limit 0. We plug the 5 into here. So we get 6 times 5 cubed over 3 plus c minus f of 0. That'll be 6 times 0 cubed over 3 plus c. Simplifying the 6 over 3, we get 2. And we have 5 cubed, which is 125. And together those make 250 square units. Again, that's something we could not have computed earlier because it's the area under a curved shape, which doesn't have a standard area formula. Let's go back again. Again, emphasizing the major progress we've made here. That is the area under a curved function that is not a circle nor made of rectangles, and we still can get an exact value for that through this calculus process of finding the antiderivative of the boundary of our area.